Let's take a look at our first example, a very simple system where water flows in and out of a tank. The tank can be assumed to be of circular cross section, and some of the variables that are relevant to the system is highlighted in the figure there. So what we have here as an example is one inlet stream and one outlet stream of water, right? So simple water in the system, and we assume that there are no temperature changes. That means the density of the different streams is the same, right? Because the temperature doesn't change and density is a function of temperature, and since temperature doesn't change, according to our assumption, which has to come from what is relevant and true for the system. So we cannot make some strange assumptions. We should be able to defend our assumptions. So here I'm just going to assume that the temperature changes are negligible, and therefore every stream, this stream, and the tank contents all have the same density, right? Which we can use the symbol rho. So the density is constant in all the streams. So given these assumptions, right? This is the configuration of the tank, and these are some of the assumptions we make. Then we just to start off things, we can just assume the units and the description of the different variables in the system. So Q1 is the volumetric flow rate of water entering the tank. So that's this Q1. The units is meter cube per minute. So you can understand, right? Volumetric flow rate, right? So the units of volume we consider is meter cube. Therefore, the volumetric flow rate will be in meter cube per minute. The same thing for Q2. So Q2 is also the volumetric flow rate of water leaving the tank, and the units is meter cube per minute. The cross-sectional area of the tank is denoted by the symbol A, right? So that's the cross-sectional area of the tank, and the units will be meter squared. The height of water in the tank, right, from the bottom till the the upper point to which the water is there at any point in time, we denote the height of water in the tank to be h, right, in meters. So the volume of water in the tank at any time is A times h, right? We assume uniform cross-sectional area. Therefore, A multiplied by h will be the volume at any time. So to be more explicit, we can write the volume of water in the tank at any time t. So this is not V multiplied by t, this is V, the volume at any time t. That is going to be equal to A times the height at any time t. So the area is constant, it is not going to change with time. So A is like a constant, so that does not involve t, right, in this particular case. So the volume at any time t is the area, cross-sectional area A, multiplied by the height of liquid in the tank at any time t. So this is the idea. So the volume of water in the tank, as I said, is going to be A times h, and the units of volume is going to be meter cube. So usually, right, whenever we are working on a system, we will do a sketch of what the system looks like, right? So that is the first thing that we do. And here we write a simple sketch or a schematic of the system. Then we write the key variables in the system, right? So I've written 4 here, and volume is A times h. So we can list out some of the main variables in the schematic. And then we will have to write our assumptions. And to be just careful with writing the correct model, we'll always indicate the units of the different variables so that we can always look for unit consistency or dimensional consistency whenever we write the equations. Now, the trick here is always to do the following, right? We always observe the system for a short time, delta t time units. So we start looking at the system at time t, that is the time we start focusing our attention on the system and the variables that are of interest to us in the system. Then we look for, or we look at the system for delta t time units. That's our attention span. That means we stop looking at the system at t plus delta t. So this is the start time, this is the end time, and therefore the duration is of observation of the system is delta t. So just typo here. So this is not capital DT. This is delta T. So I have to convert this D into this Greek symbol, right? So basically it's T plus delta T. Kindly make note of that. So now mass is conserved. Here we are not considering energy balance because we said there are no temperature effects involved, right? Temperature changes don't occur in the system. Therefore, in this system, we would just write the mass balance equation. So to write the mass balance for water in the system, we say, well, let's take the inventory or the amount of water, the mass of water in the tank at the end of the time interval, right? That means the mass of water in tank at time t plus delta t. How much of water in kilograms there is at the time t plus delta t. Then we also take into account what was the mass of water in the system at the beginning of our observation period. That means what was the mass of water in tank at time t. So what would the difference give us? The difference between the mass of water in tank at time t plus delta t minus the mass of water in tank at time t will tell us how much water has accumulated in the system, how much mass of water has accumulated in the system during this time interval delta t. So that is the physical meaning of this, right? Now, we will also say in this time interval delta t, how much of water came into the system. So this is the input term. How much of water came into the tank via the input stream during this time interval delta t. And then we subtract the mass of water that has left the system during the time interval delta t. So during this time duration of delta t, some water has come into the system, some water has left the system. So that is what these two terms stand for. So there is no consumption of water in the system. There is no formation of water in the system. So we do not have the consumption term and formation term here. In other examples, we will see those terms appearing. But here, there is no consumption of water or there is no formation of water. So water comes in through the input, water leaves the system through the output during this time interval delta t, and the difference between the two will be the accumulation of water in the tank during this time interval. So if the input water was more than the output amount of water during this time interval delta t, the mass of water in the tank would have increased. So there would have been accumulation. But if let's say during this time interval delta t, the output stream was bigger than the input stream, then the right hand side will be negative, which means the mass of water accumulated in the tank during the time interval delta t will be negative. That generally means the water has deaccumulated in the system, right? So the water amount has decreased in the tank over this time interval. So out of the four terms, we only have input and output in this particular case. We do not have formation and the other thing, which is the consumption. All right, now from the description, we will go to the symbols. So what is the mass of water in tank at time t plus delta t? Mass is nothing but volume multiplied by density. So I can write this mass of water in tank as V times rho. Volume times density at time t plus delta t. So this means volume times density, which is the mass of water in the tank at time t plus delta t. So if you put this vertical line and say t plus delta t there, it means whatever is this quantity, V times rho at time t plus delta t, minus this term, right? What is the mass of water in tank at time t? So mass is always V times rho in terms of symbols. And to indicate the time at which we are taking the inventory, we say V rho at time t. So that is this term. So this would be the mass of water in tank at time t plus delta t. This would be the amount of water in the tank, mass of water in the tank at time t. The difference is the mass of water accumulated in the tank during the time interval delta t. So that is what this is. Now if you come to the right hand side, right, how much of water has entered the tank during this time interval delta t? So the flow rate of let's look at the input stream or the inlet stream. So Q1, right? That is what we had in the diagram. This is Q1. That's the inlet flow rate, volumetric flow rate. So this is going to be in meter cube, let's say, per minute. Now, if you multiply it with density, we are going to have density is kgs per meter cube. So if you multiply the two, Q1 times rho, we will get kgs per minute. That's the mass flow rate. The left-hand side has the units of kilograms because volume times density is kilograms, the mass. So the right-hand side, if you just multiply Q1 multiplied by rho, that gives you the mass flow rate of the inlet stream. If you multiply that by delta T, which has got the units of minute time, right? Units of time, which is minutes in this example. So minute and minute will cancel, meter cube and meter cube will cancel, you will get kilograms. So Q1 rho delta T gives us the mass of water that has entered the tank during the time interval delta T. So Q1 rho delta T is this term minus mass of water that has left the tank during the time interval delta T. A very similar idea. The stream that is flowing out is flown out with a flow rate of Q2. That's the symbol. So it is going to be Q2 multiplied by rho multiplied by delta T. That is going to be the mass of water that has left the tank during this time interval delta T. So if you take the delta T outside, you can write the right hand side term as Q1 rho minus Q2 rho or the whole thing multiplied by delta T. So I hope this equation makes sense, right? So the trick is we observe the system for delta T time units between time T and T plus delta T. Then we say, what is the mass of water in the tank at time T plus delta T, the final time minus the mass of water at the initial time. The difference must have come from the imbalance between the inflows and the outflows, right? It is very much like our bank account. What is the amount of money we have in our bank balance at the end of the month minus the amount of dollars that we had at the beginning of the month? All right, that should equal our income minus expenses. So that's a similar idea. We can have money formation because banks give interest that will lead to the formation of money, right? So that is something. Then service charges would be the consumption. So if you don't have any service charges, if the interest is low, usually it is painfully low. So you can ignore those terms, right? For example, and then you can say the increase of my bank balance or decrease of my bank balance for the month is equal to the income during that time period minus the expenses during that time period. It is exactly the same idea. So in terms of symbols, we could write it in this particular fashion. Both sides have dimensionality of kilograms because we are writing the conservation of mass equation here. Now, then what you do is you can divide throughout by rho because rho is featuring in every term, right? So I'm just going to divide by rho throughout. So I'm going to get Vt plus delta T, the volume at time T plus delta T minus the volume at time T will be equal to Q1 minus Q2 times delta T, right? So I'm dividing throughout by rho. I assume rho to be constant and rho is not equal to 0. Therefore, I can do that. I get this. So what does this say? The change in the amount of volume of water in the tank over this time interval, that is this value. That change in volume has happened because there has been a imbalance between the inflow and the outflow. If Q1 is equal to Q2, the right hand side will be 0. Therefore, the volume of water in tank at time T plus delta T will be the same as the volume of water in the tank at time T. That means if your income and expenditure are equal, then the bank balance will not change. That is steady state. All right. So I hope you understand this statement. And then we can divide throughout by delta T and write V at T plus delta T minus V at T divided by delta T is equal to Q1 minus Q2. And that is what is written right here. Now then we invoke calculus, right? In the limit that delta T tends to 0, right? As delta T goes to 0. So we invoke Newton's calculus, right? To say as delta t tends to 0, this term will tend to nothing but dv by dt. So this is how the rate of change of a variable is defined, right? The derivative is defined in calculus, dv by dt. So this equation becomes dv by dt is equal to q1 minus q2. The rate of change of volume equals the imbalance between the inflow and the outflow. We can now use V is equal to A times H and write this equation as dV is nothing but D times AH, because V is equal to AH. And since A is constant, we can take it out and replace dV by ADH. So when you do that, you get this equation. Now, so this is the inflow, this is the outflow, this is the accumulation term. All right. And in technical terms, right, this H will be called the state variable. Anything that is associated with d by dt, in this case H is associated with d by dt, therefore H is called a state variable. Nevertheless, a dH by dt is equal to q1 minus q2. And at steady state, dH by dt is equal to 0, which will mean q1 is equal to q2. That means the inflow and the outflow are exactly balanced at steady state. The height of water in the tank does not change. We could also say that when q1 is equal to q2, dH by dt will be equal to 0, and therefore H will be steady. Now, so we have written the mass balance equation that's relevant to the system. Now, the constitutive relationship for this model comes from fluid mechanics, where people have noted that the flow rate out of the tank, right, the outflow rate is proportional to the height of liquid in the tank to the power of n. And that value of n, right, it changes whether the flow is laminar or turbulent, etc. So basically the idea is, if you have more water in the tank, if the height is more, the flow here will also be more, right? So if this increases because of the hydrostatic head, right? So if the height is the height of liquid in the tank is very much, right, is big, then the pressure here, the pressure difference between this point and this point will be quite high. That leads to this flow being high. And if height becomes small, Q2 will become small. And if height goes to 0, Q2 will go to 0, as you can imagine. So the question is, what is the kind of relationship really? So we know that if H increases, Q2 increases. But does it increase linearly or non-linearly? That's a different matter. That depends on the flow properties. So in general, we can write by substituting Q2 is equal to KH to the power of n, we can write the mass balance equation that we had before. You could modify that by incorporating Q2 is equal to KH to the power of n in this particular way. Now, this is a complete model. So Q1 is the flow rate of the inlet stream, and the system variable or the state in the system, right? The state variable is H. So given the values of system parameters K, right? So we have to find out what is this value of K, this proportionality constant in this constitutive relationship. So what's the value of K? We can get that from experimental data or through correlations that are available in the literature. If you know A. So A and K are the system parameters. H is the state variable. And Q1 is what is called the input variable or the manipulated variable. So you can kind of control the height of water in the system by this following procedure. So this is the water, right, tank. So this is Q2, where Q2 is KH to the power of n. N could be 1, for example. So this height of water in the tank is H. This is the cross-sectional area A. This is the inflow Q1, right? So this is Q1. So what you can do is you can measure this height, right? So you can measure this height from using a sensor, like a level sensor. So you measure the actual height, and then you can compare this height with the target height, or what is called the set point or the target. So this is nothing but the target height, the level at which you want the water to be in the system. So you can compare this. So this is the plus sign, this is a minus sign. So if there is a difference between HS and H, H is the actual height that you measure currently. HS is where you want it to be. That's the target height. The difference, right, can be processed by a controller, a control system, and that controller will adjust a valve on the inlet line. So this is what is called feedback control. You measure the state variable and you compare the measurement with the target value, and then you send this gap or the error E to a controller. So this is like a computer or a simple hardware that will adjust the valve opening on the inlet stream. So Q1 is often called the manipulated variable because you can manipulate the system to achieve its goal of a particular height h of liquid in the tank by adjusting Q1. So if the height is more than the desired height, what you would do is you will close the inlet valve. And if the actual height is smaller than the desired height, that means you want more inventory of water in the tank, you will open the inlet valve a bit more so that more water comes in and the level of water in the tank rises, right? So H is a state variable because it is associated with d by dt. And since you measure H using a level sensor, H is also called the output variable here. So these are technicalities. If you are interested, you can bother about it. But otherwise, you can just say, well, the model of the system is A dH by dt is equal to Q1 minus KH to the power of n. And we are done with that. Now, so the state variables of a system are variables which, if you know what they are, that means if you measure them, it gives you a good description about the entire state of the system, right? So you will find this idea of state variables in fields like thermodynamics, but also in systems engineering, process systems engineering, etc. So if you know about the states, you pretty much know about everything about the system. For example, if in the body, right, the human body, for example, if you know the pulse rate, if you know the heartbeat rate, for example, if you know the body temperature, the blood pressure, things like that, right? There are a few vital states of the human body. If you know that and they are within limits, the doctor will certify you as being in a normal state, right? That means everything seems to be reasonable and the person is healthy, etc. So that is an example of the state variable, right? Sometimes you can also look at blood glucose value for the individual, right? So that is also a state. So some states are easily measured using sensors like thermometers. Some states you have to probably use some advanced sensors, draw out fluids from the body, etc., to find out the values of the states. But once you know those states, then you know whether a system is good or not good, etc. Now, typically, right, we may just measure a few states of the process. So if you take a distillation column, the distillation column has several trays. So this is a distillation column, feed entering somewhere, and there are trays, right? There are trays in a distillation column, and then there is a reflux drum, and then it reflects. This is the distillate, and then in the bottom side you have this reboiler where you supply energy, and then you create vapor and send it to the vessel. So the vapor flows in this direction, the liquid flows in this direction. There's mass transfer happening, and that leads to separation of products, etc. Right? So you can have composition or temperature on all these trays, right? So those are all the internal states of the system. But you will not measure all of them. You will measure some tray temperatures. You may measure the composition here. You may measure the height of the contents of this reflux drum. So you may measure only a few of the states. You may not measure all the states of a system because sometimes they may not be accessible. Sometimes you don't have to do it. All right. So that is the idea. Now, in general, right, you can have a system which is described like this. So if you take a look at this particular system, x1 and x2 are variables associated with d by dt. So x1 and x2 are called the states, or they're called the state variables. U is what is called the manipulated variable. I can use U in order to reach the state that I want to reach, right? For example, the level of water in the tank, I can manipulate Q1 and then reach the desired height. Likewise, in a general system description, this U is called the manipulated variable. And in this example, Y is called the output variable because it is a combination of the states. So whenever I need an output, I have to have a sensor of some kind that will measure the value of that state. And once you put a sensor and you measure the state, that variable becomes an output variable as well. Here, they have a sensor that measures 3x1 minus 2x2. So it's a linear combination of the states that the sensor is measuring. It's like measuring the differential pressure, which is the difference between two pressures, right? So pressure at one point, pressure at other point are two states of the system. And then the differential pressure transmitter will measure and transmit the differential pressure, the difference between the two pressures. So Y can be treated something like that. I'll stop here before we embark on the next example in a future video. Thank you.